Let's take a look at 33. So we're dealing with end behavior. Make sure you understand the concept. What is this going on here? What is it saying?
No. The image is small. It is projected as a trapezoid.
Oh. There we go. Okay. So here we go. When we're looking at stuff like 23, you need to have a good conceptual understanding what end behavior is. End behavior means when x gets really, really super large. 10, 20, 30, 40, 50. So to the end of the function, when I'm plugging in huge values, what happens? Well, this one, you don't need a graph. You can kind of picture what's going on. When the bottom of that fraction gets big, what's this getting closer and closer and closer to? 0. Negative 24 over 100. Negative 24 over a million. I'm quizzing here. Negative 24 over a billion. Exactly. Exactly. No. Then we're getting closer and closer and closer to 0. Okay? Now, what if I went to negative infinity? Negative infinity would be like negative 100, negative 1,000, negative 1,000,000. We'd still be getting closer to 0, but from the positive side instead of the negative side. So if I was going to graph that, the way that might look in that section is this. It might look like this, where it's getting closer to 0, but from the negative side. This one's getting closer to 0, but from the positive side. But they're still getting closer to 0. But you've got to understand that we're looking at the outer left and right as to what's happening with this function. 37, was that the next one? I should have assigned 35 also. I did. Okay. Okay. Oh, I didn't assign 33? No. Okay, good, because that wasn't a very good problem. But it was a good warm-up. 35. If I plug in 10, I get 11 over 8. If I plug in 100, I get 101 over 98. 101 over 98, that's basically really close to 1. Yeah?
Okay, I'm just a little confused about what our answer, like, what would the answer look like? Does that make sense? Right?
Oh, yeah, exactly. Thank you. The end behavior. Okay, so that's a great question. Everybody say thank you, Hunter.
Thank you, Hunter.
Okay. Well, on these things, I think you can look in the back and kind of see how they have it written. But here's how I would write it. What I would do, like on a quiz or something, is I would say as x approaches negative infinity, then what happens to f of x? And then as x approaches infinity, what would happen to f of x? So like on 33, it would have been as I plug in smaller numbers, I get 0. As I plug in bigger and bigger and bigger numbers, I get 0 as well. So that's what it would look like. Okay? But you need to tell me whether you're plugging in big positives or big negatives. So when I look at 35, it's going to be the same from either side. Yes. As x approaches negative infinity, it's going to be, I'm going to go f of x. Sorry, I'm trying to hurry, and then I start getting sloppy. Okay?
It gets closer to 1.
It gets closer to 1. Is positive infinity any different?
No.
No, it is not. Okay? But here's my deal. Okay? Here's what I want you to think about. When I plug in numbers that are bigger and 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 bigger, does this plus 1 really make that much difference? No. Does the minus 2 really make that much difference? No. So what you have is you have this battle between your numerator and your denominator. They're both getting bigger, they're both getting bigger, they're both getting bigger. And the plus 1, who cares? A 1,000,001? 999,998? It's basically 1. Okay? So what you can do on these things is you can look at the highest power of x and see who's going to win that battle. It's basically x over x, which is
1.
1. That's why your end behavior is 1. So now if we take a look at at 37, it's a battle going on here. Huge battle going on here. If I plug in 10, well, yeah, the top's going to give me like 500. But on the bottom, if I plug in 10, it's going to give me like 1,000 something. Who's going to win this battle, the top or the bottom? The bottom's going to win the battle, something fierce. So when the numbers get huge, when the numbers get huge, this is getting closer and closer and closer to 0, believe it or not. Why? Because the bottom is getting huge. And the top's just getting big. Whenever you have a fraction where the top is getting, or the bottom is getting really, really big, and the top isn't keeping up with it, you're getting closer to 0. I just wanted you guys to think about that logically. But right now, I won't put anything like that on the test, but realize if I give you something like any of these graphs, you need to tell me what the end behavior is on any of these graphs. So,
Can we go over one of those?
tomorrow, get your questions ready. Get your questions ready. Okay. So, do we have anything we want to talk about from specific assignments before I go on to new information?
Is this new information?
Yes. That's why I want the time to do a great job talking about it today. Let's get ready to... Okay.
1 billion. They could.
He's a trillion.
Oh my god.
Here we go. Today. Uh-oh. Gosh dang it. I'm rubbing my eye. Just to let you know, you can, in fact, catch pink eye or conjunctivitis from your dog.
What? You got pink eye?
Yeah. I had to take my dog to the vet on Friday, and Sunday morning I woke up and this eye was all red and swollen. Went to urgent care and they go, oh yeah, you've got conjunctivitis. So they put me on pills, and I've been on it, or not pills, but drops. I've been on them for 48 hours, so I'm supposed to be non-contagious anymore, but I'm still just being uber careful. Okay. So 1.4, extrema.
Extreme.
Yes. Extreme is the thing you need to think about. Okay? What are my extremes going on here? And actually, I'm going to give you kind of a funky graph that we're going to use for the first 3 or 4 examples. So let me just spend some time making a graph here. And the points are going to be kind of important. Yeah, I will.
What about this one? What about this one? T-A-L.
Yeah, I know this is kind of funky, but we're going to use it all, period. Okay. Let's go 3, 4. I'm sorry. It should be 7, 4. My bad. My bad.
Oh.
I made a mistake. So we got this funky graph going on. Is this graph a function? Maybe I'm doing some review for the test right now. Is this graph a function?
Yeah.
How can we tell? Because it passes the what? Vertical line test, saying that for every input we yield only one output. If I filled in this right here, that would not be a function because I'm getting 2 different answers when I plug in 7. Okay? But what I'm interested in here is my extrema. My extrema fall into a couple different categories. Okay? We have an absolute max or minimum and a relative max or min. Absolute max is just the highest it ever gets. Absolute minimum is the lowest it ever gets. Relative maximum. Do you see any points on here that might be what we consider a relative maximum? 15.3. Yeah. It's relative to its neighbors. It's the highest. It's like the tallest person in here. Not necessarily the tallest person in the school, but the tallest person in that region. Okay? So let's list all these things. Does it have an absolute maximum?
Yeah. No. Wait. 3. No, because the arrow keeps going forever.
Exactly. It has no absolute maximum.
Whole thing keeps going.
No absolute max. Does it have a relative max?
Yep.
Now, this is what we got to figure out. How are we going to phrase this? Well, the maximum is the height it's at. What is the relative maximum? No. Relative maximum is 3. When does it happen? At x equals 15.
So why is it 3, 4 instead of 5?
Well, that one, to tell you the truth, I'm not quite certain on that one. Usually when I'm talking about relative maximums and minimums, I don't put a constant function in there. But I did in this case because it's going to come up in an example later. So for the purposes of this problem, let's just ignore that little piece. Okay? But this is the relative maximum is 3 and it happens at 15. For example, don't write this down, but if I would do a graph of my weight, let's say this is 235, 50. Okay? What was my absolute maximum weight? 235. At what age did it happen? 50. That's how we need to word it. Like down here, going back down here, my relative maximum was 3, and it happened when x is 15. So my heights are what I'm looking at.
Okay, question. So,
yeah.
What's the difference between relative and absolute?
Relative is just the biggest in comparison to its neighbors. Like, say, this right here.
Oh, okay.
So if it's on like a relative.
Boom. No. Does it have an absolute minimum?
Yeah.
What is the absolute minimum? -3 at x equals 1. Good. Does it have any relative minimums?
Yeah. -3 at 1.
No, relative. Well, that's the absolute, so I'm not going to name it again. -2 at x equals 10. If we had more time, I'd make sure you could do this with a graphing calculator. But I don't want to address that right now with the limited time we have. What?
Because I see what you're saying.
Oh, I see what you're saying. I see what you're saying. But this right here is not a relative minimum. No. If anything, this might be a relative maximum, but we're just deal with humps. You'll see what I'm talking about here when I get to just the next part, why I did this. In hindsight, I probably should have just taken the time and done a second graph. So maximums, minimums, if I would give you a graph like this, I would anticipate you to be able to give me where the relative maximum minimums occur. Okay? But of course, this doesn't have specific points. But one thing I want to show you is this. Here's the definition.
F of A is a relative maximum of f if there exists an interval x sub 1, x sub 2 containing A such that f of A is bigger than f of x for every x is not equal to A in the interval x sub 1 to x sub 2.
Does that make sense? So let me show you what they're talking about. They're saying, here's the interval from one value of x to the next. So those might be like right here. And there's some value of A which that its value is bigger than all the rest. Where its result is bigger than all the rest. That's the technical definition of that maximum. Yeah. Okay. So anyway. So like at this point, here we go. Hello. Like this one, I would expect you to be able to estimate the relative maximums and minimums. Okay, and you'll do that tonight. If we have time, we'll come back and we'll talk about the graphing calculator. Okay. So in intervals, next thing. Yeah, because I zoomed in way too much. Intervals of increase and decrease. Intervals of increase and decrease. Well, if I would go back to my weight deal. When was my weight increasing? From 30 to 50. That interval, right? So if we wanted to write that in mathematical terms, we could say it's increasing from 30 to 50 using our interval notation. Right? Okay. Where was it decreasing? From 50 to 56. And we could write the interval for that. Well, let's go over here and let's talk about where it's increasing and decreasing. Hold on, let me just look at one thing here real quick. Okay.
So when you do this, are you only going to put like y's together and only put x's together?
Well, you'll see. So like in this one, let's go back to here. Where is my function increasing? From 1 to 3.
Yeah. 10 to 15.
And also 10 to 15. So now these are intervals. These are not ordered pairs. This is it. It's increasing from 1 to 3 from x because we're scanning this. Oh, it's increasing there. And it's increasing there. And it's really kind of goofy to say it's increasing at the very, very, very end. So we're just going to do soft parentheses on everything. That's fine. Decreasing. Where's it decreasing?
15 to infinity.
Okay, 15 to infinity. That's one of them.
Infinity to 1.
From infinity to 1.
7 to 10.
Okay, I think that's where it's decreasing. And there's one other category we need to be able to describe. It's where it's constant.
8, 3, 3. Wait, no, it's 3, 3.
Okay. 37.
Oh. It was just confused.
Yeah, since I wrote it down wrong to start with.
Wait.
No, because we're looking at the y values. Like think back to my weight. If my weight was steady, we'd say my weight was constant from 3 to. Okay. No, you're fine. Hey, I'm glad you're working through that. That's good. Okay. So on that right there, you want to talk about funky definitions? Okay. Function is increasing on an interval I if and only if for any 2 points in I, a positive change in x results in a positive change in y. That kind of makes sense, I think. If you increase the x, your y increases. Now, in math terms, what do we have to say? For every x sub 1 and x sub 2 in the interval I, f of x sub 1 is less than f of x sub 2 when x sub 1 is less than f of x sub 2. Or x sub 2.
Yeah, you've lost.
What this means is, I think they should have wrote it the other backwards, but it says a smaller result happens when you plug in smaller numbers. That's what it's saying. When you plug in bigger numbers, you get bigger results. I'm not going to throw this on a test or something, but this is what you're going to see in college. You're going to have somebody up front that probably speaks a different language. This is decreasing when these get bigger. Trust me, it's kind of weird. So let's look at the next one. For every x of 1 and x of 2 in the interval I, f of x of 1 is greater than f of x of 2 when x of 1 is less than x of 2. What does this mean? Well, let's go backwards. I think they should have wrote this part first. When I plug in a smaller number, I get a
Small result.
no,
Big result.
a bigger result.
Oh.
So when my results get bigger, my inputs get smaller. And then, gee, the last one, that should be no surprise. Whatever the heck I plug in, my results are
Equal.
They're the same. Okay, I always have to redirect you. I wonder how much time we lose from me trying to redirect you guys back in. That's why we're only on section 4 right now. Rate of change. Yep, I will. Rate of change is just, honestly, when I think of this, it's the one thing you can relate to before slope. Okay? So usually what you've said with slope is the change in y over the change in x, or my rise over run. Well, now it's going to be something more, a little bit more elegant. It might be like the change in height over the change in time. Okay? So like this one might be, it went up 60 feet in 3 seconds, then my rate of change is 20 feet per second. So our rate of change, we're trying to see how the result of my function compares with my input of my function. Okay? So here we go. Let's do this. Find the average, and I'm going to go ROC, rate of change, of f of x and over the interval -2 to -1. The reason why I have to say over an interval is this a straight line? No, it's not a straight line. So its slope or its rate of change is going to be different everywhere. So this is laying the groundwork for calculus. So what we're going to do here is we're going to find f of -2, and we're going to find f of -1. Okay? So plug in -2, plug in -1. Let's go, ladies, -2, guys, -1. Go. Ladies, -2, guys, -1. -4?
No. Three times negative. Yeah, you're wrong. Negative one. I said, maybe we got -2 pushing. And still trying to figure out the negative bracket.
This is not a calculator problem, by the way.
Okay, so it's 4.
Yeah, yeah, there you go.
-2 cubed, that's 8. I didn't see the 4.
Yeah. And look where I'm doing my work. It's right next to f of -1. Ladies, what'd you get? 2. So we get negative of -8, so we get 8 plus -6 equals 2. So here's the thing. Let's turn this into something you've done before. My x and my y, -2, 2, and then I have -1, -2. Would you guys agree with these 2 points? Do you guys agree that these two points are correct because I plug in -2 and get out 2? I plug in -1 and get out -2. Okay, so now we just got to find the slope or the rate of change. So once I have these 2 bits of information, it should become pretty straightforward. Okay, let's go this way. 2 minus -2 over -2 minus -1. 4 over -1 gives me -4.
Hey. -4.
Yeah, you were just ahead of everybody, Eddie. Okay? So, average rate of change. Okay? This actually, a sport that I'm really interested in is drag racing. We watched a lot of drag racing this weekend. U.S. Nationals were yesterday. And what they do is they take a 20-foot long section of the track and they find the average speed over that 20-foot long section. And what they do is they take, okay, this is 1,000 feet, this is 980 feet, and then we have the time difference between the two, and they do this. And one of the cars this weekend went from a standing start to 1,000 feet, which is a 300 meters on your track. They accelerate up to 343 miles an hour, which is straight up moving. 3.6 seconds. They go from 0 to 100 in under a second. So here we go. So on this, summarize. Find f of negative 2. Find f of negative 1. Okay? So this is what we were doing. Set them up as points, and then you can go ahead and use your old skills of the slope, and you'll get the same thing. Okay? So here we go. Let's be ready to go. Let's... Okay. Page 40. Numbers. One, 5, 7. Get started on that. I'll spend a little bit more time on this. Shut up. Jesus.
Wake if you lay down on a big thing.
That's a good call.
Yeah, big thing.
That's a new one. It's very good.
It's like a big thing.
We're going to start a new habit. I'll just keep adding to the assignment until you guys shut up and get to work. Sound good, Gigi?
Nope.
There you go. I could have said that to about 4 different people. Maybe it's going to take a good, strong test to get everybody to kind of step up a little bit.
So tomorrow we can come back with any page number.
Yeah, you bet. You bet. Be ready to go, and I'll answer, and we can grab whiteboards. We can do whatever you want.
Jeffrey.
No.
Okay.
You're looking at these. You're looking at x's. Remember, you're telling a story from this value of x to this value of x. It's increasing. From this value of x to that value of x. And if you're not quite sure, take a look in the back and see what they're doing. I think my drill story.
Or
No,
depending, like
it's still x's. It's still because it's constant from 3 to 7. You know, it's constant from deducted. Eddie, where were you Thursday, Friday?
Thursday, I was going to do my ear infection, and Friday, I was going to Minneapolis.
Okay.